Hello, my name is Lillian Wilson Wade, and this is the third Physics 2 lab examining the magnetic field of a bar magnet. The purpose of this lab is to measure the distance dependence of the magnetic field due to a small bar magnet. We'll also be comparing the measurements to the distance dependence predicted by the equations for the on and off axis or perpendicular magnetic fields derived from the Biot-Savart law. In my results, I found the distance dependence to be n equals negative 2.7935. and my magnetic dipole moment to be 3.177 ampere meters squared. Before we get into this experiment, let's first review the fundamental physics principles that relate to this lab. Like I said in the beginning, we'll be utilizing the Biot-Savart law, which describes a magnetic field generated by an electric current. We'll also be using these formulas to calculate the distance dependence, which is denoted by n. And in addition, we will need to know and understand the changes being on or off axis makes to the calculation of the magnetic field at an observation location. To collect data in this experiment, the magnetometer app was used to calculate the net magnetic field and x, y, z components of the field. The data in the top left displays the measurements for the magnetic field on axis, and on the bottom, the measurements for the magnetic field perpendicular or off axis to the magnet. I found the average distance from the magnet to the sensor that produces a magnetic field with an x component of magnitudes 20, 70, 120, 170, and 220 microteslas while on axis. You can see all this information, like I said, again, on the left. I use that information to then create the graph to the right, which plots the linearized magnetic field against the linearized distance. This line of best fit formula will help us determine and calculate the distance dependence and the magnetic moment. And the distance dependence is actually equal to the slope of this graph. As I stated before, the slope of this line is equal to the n value, the distance dependence. From that equation, we also know the value of B, which is the equation's y-intercept. So the magnetic field's value of B is negative 14.269. So next, we're going to use the Biot-Savart law to calculate the magnetic dipole moment. First, I solved for K by plugging in the known values of R, N, and B into the linearized Biot-Savart formula. I found K to be approximately 6.354 times 10 to the negative 7. Next, I set the magnitude of B bar equal to mu naught over 4 pi times 2 mu over R to the third. I solved for mu and found its value to be 3.177 ampere meters squared. Before I go any further into this lab, let's review my observations from the actual conduction of the experiment. I found that when the magnetometer app is far away from the magnet, it measures a near zero magnetic field in the x direction, and as we move that sensor closer and closer to the magnet, the measured x component of the magnetic field increases. Next, I'll get into my visual model and Glowstrip code. Here you can see the code that built my visual model. I created a function to calculate the magnetic field that was iterated over several locations. I also created 2 on-axis and 4 perpendicular observation locations in the code. Each location calculates its own net magnetic field, and then I calculated the value of the magnetic field in an observation location at a 45-degree angle from the magnet. Here's my Glowstrip model. You can see that the white cylinder represents the bar magnet. The blue arrows represent the magnitude and direction of the perpendicular or off-axis magnetic field. The orange arrows represent the magnitude and distance of the on-axis magnetic field. And the pink arrow represents the magnitude and distance of the magnetic field at an observation location 45 degrees from the axis. You can also find the actual calculated values of all of those fields at each observation location in the bottom left. To conclude this lab, let's answer some final questions. So what if we hadn't oriented the experiment to compensate for magnetic north and had instead laid out the meter stick at some intermediate angle with respect to Earth's magnetic field? How would the results have changed? So neglecting to compensate for our experiments for the magnetic field of the Earth in our experiment would have a major impact on the calculations. The presence of the Earth's magnetic field would have particularly changed the value that we got for the X component of the net magnetic field. And what if we were to stick 2 identical magnets together end to end and run the experiment again? How would we expect our measurements to differ? Well, sticking together those 2 magnets would have produced a more powerful magnetic field, while the magnetic field magnitude of that magnetic field would change and obviously increase. The direction would still stay the same, however. So thank you so much for watching this lab, and I look forward to completing lab 4. Thanks.